Welcome back. One way to help ground our understanding of the derivative is to think about position versus velocity. So one thing to note is that velocity is the rate at which the position function changes. So in other words, velocity, if we use v for representing that velocity function, so v of t represents the velocity function, is equal to the derivative of the position function. Because the derivative, again, represents the rate of change. And so if velocity is the rate at which the position function changes, then velocity in terms of a function can be written as the derivative of the position function. So this also means that the velocity function is giving you the slope of the tangent line of the position function. So this is really helpful to understanding the derivative a little bit better. And we're going to use this velocity and position example in many different cases going forward, especially when we talk about integration, which is the reverse process of the derivative down the line. There, the position and velocity example will come in handy. So in example 6, suppose a robot moves back and forth along a line, and that the position of the robot in meters over time t in seconds, is given by the function s of t to the right. So here's our s, this is the position, and then t is the x-axis. And so we have the position of the robot at any given time t. So you can see that the robot initially has a position of 1, and then it stays at 1 for the first 2 seconds, and then it decides to move, has some coffee, and starts moving over to a position of 3, stays at 3, then it moves to a position of -1, and then it moves back to a position of 0. I guess it never really was, except for right here, but goes to a position of 0. So anyway, this position function is tracking the position of the robot at any given time t. And here we're imagining that the robot is actually like over here on the number line and is moving up to here to 3, and it moves back down to -1. It's moving back and forth along the some kind of line. So you can imagine it's moving back and forth along the y-axis. But this dimension is giving you a sense of time. So the first job is to graph the velocity function v of t, and there's a space down below to do that. So here on the y-axis we have velocity. Well, the velocity is going to be the rate at which the position function is changing at any time. And if you look at the first 2 seconds, what is the velocity in the first 2 seconds? If you said 0, that would be correct. The robot is not moving, so the change in position is 0 meters per second. So I'm going to draw a 0 line, and at the beginning and end I'm going to put these little open circles. And this is because we're going to have some sharp changes in our velocity, and when we have those sharp changes, it's going to be hard to know at that particular t value if the robot is not moving or if it is moving, because it's suddenly going to change from not moving to moving in an instant of time. So I'm going to put these little open circles to say we don't really know what's going on at t equals 2, like at that instant. We don't know what the velocity is, but we know that immediately after, the velocity, the robot is going to start to move. It's starting to move to position 3. So it's going to have some velocity. So what is that velocity? If you think about what is the velocity? Well, how far does the robot move on this interval of time from t equals 2 to t equals 3? How far does the robot move? If you said 2 meters, that would be correct. It moves 2 meters. It kind of goes up here, a distance of 2 meters. You can do 3 minus 1 to figure that out. And then what's the elapsed time? If you said 1 second, that would be right. So the average speed then from t equals 2 to t equals 3 is 2 meters divided by 1 second. That's 2 meters per second. That's going to be the average speed from t equals 2 to t equals 3. And it's the constant 2 meters per second. It's a constant 2 meters per second that it's traveling at. another way of thinking about this is we just found the slope of the secant line going from this point at t equals 2 to this point at t equals 3. The secant line would be running through those 2 points. And the slope of the secant line is going to be 2. Now, the thing is, the secant line happens to coincide with the tangent line at any given point here, right? If you pick a point right here and you draw the tangent line is going to have the same slope as the secant line. It's going to have slope 2. So that's why at any given instant in time, we can say that the slope of the tangent line is 2, and therefore the velocity is 2 meters per second at any instant in time from t equals 2 to t equals 3. What about from t equals 3 to t equals 4? What's the velocity? If you said 0, that would be correct. Because the robot's not moving, it's moving at 0 meters per second. What about from t equals 4 to t equals 6? That seems to be some movement going on there with the robot. So from this point to this point, what's the velocity going to be? Well, here, if you calculate the change in position, it's negative. So it's going to be negative 1, 2, 3, 4. So it looks like from here down to here, it's negative 4 meters. Here, velocity has a sense of direction, and so that's where the positive and the negative are going to give us is the direction. One's going up and one's going down in our orientation here. And then what's the elapsed time from t equals 4 to t equals 6? 2 seconds. So what's the velocity on that whole time interval? If you said negative 2, that would be correct. Negative 4 divided by 2 would give you negative 2 meters per second. What about on that last time interval from t equals 6 to t equals 8? What's the slope of the secant line going to be there? Well, it looks like it's 1 over 2. 1 meter over 2 seconds. And the slope of the secant line is going to coincide with the slope of the tangent line if you're dealing with a line connecting these 2 points. And so we're going to have that constant velocity of 1/2 meter per second. So it's again a rise over run to figure that out. Now, if the curve between these 2 points were different, let's say it went like this, well, then we don't have a constant velocity. Then it's not really going very fast at the beginning, but then it kind of speeds up right here as the position changes faster. And then you're dealing with something more like this. It would be the velocity would be increasing faster over that interval. It would no longer be constant, like a constant 1/2. But when you're dealing with straight lines for your position function, then you're going to be dealing with constant velocities because lines have a constant rate of change. So now we can use this information that we just put together in this graph to help us answer B through E. B says find the derivative of the position function at t equals 1. Well, we just found the velocity, which is the derivative of the position function. So asking what is the derivative of the position function is just like asking what is the velocity at t equals 1. So what is the velocity at t equals 1? Yeah, it's 0 meters per second. 0 meters per second. There we're just reading off, this whole graph that we just drew was the velocity function. So we're just reading off what the velocity is, what the y value of this graph is when t equals 1. The y value is 0 meters per second. The robot's not moving at that time, in other words. Or the position is not changing at that time. What about s prime of 5? If you said -2, that would be correct. Need -2 meters per second. We're going to make sure we put our units. What about s prime of 6? Well, there we put these open circles, and so you can write either undefined or you can write does not exist. With derivatives, you can think about it either way. You can think about the derivative as being a function, in which case the function is undefined at x equals 6. Or you can think about it as being a limit, right? By definition, the derivative is a limit. So the limit as h approaches 0. And that limit does not exist. So either way you want to write it, you can write dne or you can write undefined here is okay. Because we have that dual concept of the derivative. It's both a function, but it's also a limit. What about v of 7? There we can just look over and find out that v of 7 is 1/2 meter per second. Let's look at a graph that doesn't have lines, so that's changing a little bit more smoothly. So here's the graph of f of x, just some f of x curve in general, and below it is the graph of f prime of x. It's a little hard to see this, but this is f prime of x. So this is representing the derivative at any given point of this function. Now, one thing to note is here at the very beginning, the function has a very big positive slope tangent line. So right here, the tangent line has a very big positive slope. And if you look down, that's what we're seeing. We're seeing that the derivative is a very big positive number. I mean, well, 7's not huge, but it's, you know, fairly big or fairly steep as slopes go. So so here it's starting off as a big positive slope. And then as you move along the curve, notice that the slopes are getting not quite as steep. They're falling in value, right? And then at the top, what is the slope of the tangent line at the top? If you said 0, that would be correct. A horizontal tangent line is going to have slope 0. Horizontal lines have slope 0. If we look down, that happens right about at x equals 3. If you look down, just go straight down. These graphs are all lined up. You go straight down. Notice that this corresponds with f prime, or in other words, the derivative equaling 0. Right? This is supposed to, the f prime is representing the slope of the tangent line, and here the tangent line, slope of the tangent line is 0. So we would expect the derivative to be 0 at x equals 3. That happens over here as well. At the bottom of this curve where we have another horizontal tangent line. The tangent lines are kind of like a surfboard. You know, you're riding a wave and the surfboard is like perpendicular, or is not perpendicular, is in the same direction as the curve. So it's riding along the function like a wave, like a surfboard on a wave. Of course, the surfboard here is underwater, but I guess there's where the analogy breaks down a little bit. And there the surfboard purls and you tip over and then the wave eats you alive. Anyway, so here we have the bottom of the curve where the tangent line has slope 0. And if you look down, there the derivative is 0. And we have one more place where the tangent line has slope 0. And if we look down again, right around there, I kind of bent my line. But there's where you're going to have the derivative equal to 0 as well. And you can track a little bit in between too. Like right here, for example, we're going to have a very steep negative sloped tangent line. And if you look down, that's where you have the steepest or the smallest value for f prime. It's the lowest it ever gets, I guess you could say. So, and that's because this is where it's the steepest in the negative side. After that, it starts to, the nose of the surfboard starts to rise up to 0. So the derivative is going from some, so quote, large negative number or a very small number overall to a slope of 0 over that time interval. And then the surfboard starts to point up, and so you're going to get a positive slope from this point to this point, and we can see that positive slope from this point to this point. Okay, we'll practice a little bit more with that in future packets, like packet 14 and 15. But for now, let's finish off this packet. by mentioning that you can also talk about left and right hand derivatives. After all, limits, you can take either the regular old limit, like we've been doing, the limit as h approaches 0, or you can take a left-hand limit, the limit as h approaches 0 from the left, or a right-hand limit, the limit as h approaches 0 from the right. So you can work that derivative definition from the left side and from the right side as well. And here's how it would look visually, remembering that these are slopes of secant lines getting closer and closer to a slope of a tangent line. So here's a f of x equals x squared kind of curve. Actually, this is x squared plus 1, I just noticed. X squared plus 1. Huh, never noticed that in all these years. And so if we're taking the left-hand derivative, having h approach 0 but negative means that h is a negative value. So if you're looking at the tangent line at 0, then, like here our a value is going to be 0. Then an h value of 0 would move your other x value to the left. It would be like a negative h value. So if you do this x value plus a negative value, that moves it to the left. So your other point might be like here, and here, and here, and here, as you're choosing x values that are getting, as you're choosing your h values that are negative, but smaller and smaller, closer and closer to 0 h values. So this x value here is going to get closer and closer to the x value at which you want your point of tangency. So this point right here is anchored at the x value you're interested in. This is going to be your a value, which again is in this case is 0. But then as h is shrinking down to 0 but is negative, then these x values are going to move towards your anchor. And so these slopes of the secant lines are going to get closer and closer to the slope of this tangent line. Same exact thing happens on the right-hand derivative, but it's just the mirror image on the other side. So when we look at some various curves, we're going to see some cases where derivatives just don't exist, and it's because the left and the right hand derivatives possibly don't agree, or possibly there's some other reasons going on here. So in the case of a corner, switch back over to here. A corner is just a place where you have a part of the curve and another part of the curve, and right there where the two curves meet, the curves are having different kinds of tangent lines. So here we have a positive tangent line. Here on the curve to the right, we have this negative tangent line. And what this is representing is that the left-hand derivative, which is coming in from the left, has a positive value, but the right-hand derivative coming in from the right has some kind of negative value. The main thing is these two values are just not the same at all. And so because the left and the right-hand limits don't agree, then the regular limit as h approaches 0 does not exist, and so the derivative does not exist at that corner. A cusp is kind of like a corner, but it's infinitely sharp. So when you look at the curve coming into this point on the cusp, the slopes of the tangent lines are going to get larger and larger and larger. They're going to grow towards infinity. So if you were to draw a tangent line right here, it would be like a vertical line, and that has an undefined slope. And so because the slope of the tangent line is undefined at that point, we would say that the derivative does not exist. Going back to the left and the right hand left and the right hand derivative definitions, in each of those cases, the limit as h approaches 0 from the left, or the limit as h approaches 0 from the right of those secant slopes, those ones are going to blow up to positive infinity or maybe negative infinity from the other side. Those aren't even going to exist as numbers themselves. So definitely no derivative existing at a cusp. By the way, because of that infinite slope, these cusps are really, really dangerous. They're very sharp, so you want to be careful when you touch a cusp. Youch! All right, this one is kind of similar to the cusp in that when you have a curve, this could be a function, but right here along the function, you could have a point on the graph that has a vertical tangent line. And once again, this would have the same problem. The left-hand derivative and the right-hand derivative, in this case, would both be positive infinity. And even though they agree, they're not agreeing on any particular number. So we wouldn't say that the derivative is defined as some particular number. So we would just say that the limit is infinite, and so the derivative here does not exist. If you have a discontinuity, well, kind of like the corner, you're going to have different derivatives coming in from the left-hand side and the right-hand side. Like these derivatives on the left are going to be going from this point to a point on this left curve, and then over here on the right, the slopes of the secant lines are going to be more like negative, like this. So once again, the left and the right-hand derivatives are not going to match at all. In fact, these left-hand derivatives are going to be blowing up to infinity, in fact, so even that alone would cause cause it to not exist, cause the derivative not to exist. Okay. One more thing to mention before we finish off this packet. Let's tie together the relationship between derivatives and continuous functions. This theorem says that if f has a derivative at x equals a, then f is continuous at x equals a. So if a function has a derivative, if it's differentiable, then it's continuous. That's what this theorem is saying. Differentiable functions are continuous. And the contrapositive is also true. So if a function is not continuous at a point, like is discontinuous, that would be our picture to the right would be an example of that, then it is definitely not differentiable there. So as soon as you find an x value where the function is not continuous, where there's a gap or there's a hole in the graph, then the function is not differentiable there. So here's the proof. Suppose that f is differentiable at x equals a, then that means that by the limit definition, the limit as x approaches a of f of x minus f of a over x minus a is equal to L for some real number L. Now this is actually using a version of the limit definition of the derivative that we didn't make a lot of use out of. But remember, there was one of them that said f of b minus f of a over b minus a. That's this one, and we're just letting x, we're using x instead of b here. So this limit would, if f is differentiable at x equals a, then this limit, this derivative limit, would have to exist and be equal to some number that we're calling L. Also, if we take just the top part, take the limit of the top part, so the limit as x approaches a of f of x minus f of a, and manipulate the inside so that we multiply the top and the bottom by x minus a. So here what we're doing is trying to figure out what the difference is between f of x and f of a. This is going to help us try to figure out if f is continuous at x equals a. So we're going to multiply the top and the bottom by x minus a, and that introduces this limit of the difference quotient that we know is equal to L. So all we have to do at this point is split up the limit into the limit of the first factor times the limit of the second factor. This is using one of the limit laws. So here's the first limit times the second limit. The first limit we know is equal to L because f was differentiable, and that L was just what we called what the derivative is at x equals a. And then the second part here, the second limit, we have x approaching a. So the limit as x approaches a of x minus a. Well, there we're just going to be plugging in a in for x, because that's what x is approaching. It's approaching a. So we have a minus a, which is 0. So L times 0 then gives us 0. So that means that f of x and f of a are, the difference between those is approaching 0. These two values are getting to be the same value in the limit. So now what we can do is look at the limit as x approaches a of f of x. If the limit of the function is equal to the function value, then we'll have shown that the function is continuous at that x value. So we start off with the limit as x approaches a of f of x. We can rewrite f of x as f of a plus f of x minus f of a. This introduces a part of the limit that we just found a moment ago. We said that that was 0. So we're just kind of, it looks like we're making a big mess here. We're writing f of x as something bigger, but that's only because we know f of x minus f of a. We know what happens to that in the limit. And so then we can distribute this limit across the addition using a limit law. And we have the limit as x approaches a of f of a plus the limit as x approaches a of f of x minus f of a. And this part we figured out just above. That's 0. And the limit as x approaches a of f of a, well, f of a is just a constant. A is representing some kind of constant here. So this limit, there's no x that's changing here. So this limit is just equal to that constant. It's like taking the limit as x approaches 1,000 of 5. Well, it's just going to be 5 because 5 doesn't change no matter how x changes. So what's left over here is just f of a plus 0, which we can write as f of a. So what we've shown is that the limit is equal to, through this chain of reasoning, the function value at x equals a. And so therefore f is continuous at x equals a. And that takes us from differentiability to continuity. Okay, another long packet, but at least not as long as packet 2. Thanks for sticking in there and for watching this video, and I'll see you in the next packet. Take care.